Continuing with calculus with parametric curves, the next thing we will look at is areas. So once again, recall that for a function y equals f of x, the area under the curve from x equals a to x equals b is given by this particular integral. And the idea being that if you have a function and you go from a to b, break this function down into a bunch of rectangles, and you add up the areas of all of this rectangle, and it becomes this integral. That's something that you've learned in prior classes. So once again, we have a similar question here, like the one we tackled in the tangent video, which is what if we have a parametric curve where x is defined as some function of time or some parameter t, and y is defined as some parameter, and we want the area for t between two values, say alpha and beta. Okay, so this value, this area normally would be given by y dx going from a to b, but in the parametric form, this will be given as going from alpha to beta, and we have g of t, which is your y, and we have f prime of t dt, which is basically dx. So all we are doing here is we're taking y, we're replacing y by gt, and we're taking dx and we're replacing that by f prime t dt. So let's look at an application of this problem. This one is pretty straightforward. Suppose says find the area under one arc of the cycloid given by x equals r theta minus sine theta and y equals r 1 minus cosine theta. Here the parameter is called theta instead of t, where theta is the angle for the arcoid, for the cycloid that we have seen in our previous lecture. Okay, now one arc of a cycloid is given by 0 to pi r. So one arc means that the angle theta goes between 0 and 2 pi. So just based on this particular formula over here, we have that the area is going to be 0 to 2 pi. Then we have y, which is r 1 minus cosine theta, and we have the dx, f prime t dt, which is going to be r theta minus, this is going to be r 1 minus cosine theta, because the derivative of theta is 1 and the derivative of sine theta is cosine theta. So this becomes 0 to 2 pi r squared 1 minus cosine theta squared d theta. Now r is a constant with respect to this particular variable, which is theta. Expanding this, you get 1 plus cosine squared minus 2 cosine theta d theta. And each of these has its own way of working out, right? So you have 0 to pi d theta, that's simple. Then you have let's do the -2, 0 to 2 pi cosine theta d theta. That's also straightforward because the antiderivative of cosine theta is negative sine theta. But for cosine squared theta, we will use a trick that you have seen before, which is we will use the half angle formula, right? So we will rewrite this as 1/2 1 plus cosine 2 theta, and the integral of this from 0 to 2 pi d theta. So we have r squared. We can already evaluate some of these integrals. This will just give me theta from 0 to 2 pi. Then I have -2 sine theta and 0 to 2 pi. Then the first one is going to give me another half theta from 0 to 2 pi. And 1/2 cosine 2 theta is going to give me 1/2 negative sine. Oh, sorry. Cosine is positive sine. Sine 2 theta divided by 2 from 0 to 2 pi. So plugging all these stuff, I have, so theta and half theta can be combined, 3 theta over 2, and then a 2 sine theta, and then a sine 2 theta over 4, and all of this between 0 and 2 pi. Now, when I plug in 2 pi, I get 3 pi, and this becomes 0, because sine is 0 at 2 pi's. And subtract a 0, and again at 0, all of the sine values are 0. So all of this really comes down to simply 3 pi r squared. Okay, so nothing much in terms of new here, as long as you are comfortable doing the integrals, which is something you've done before. There is nothing new as an idea in this particular topic. So that's it for this video.